You settle into the quiet of your evening, letting your shoulders sink just a little deeper, and you picture the universe the way you've always imagined it. A dark sky, a handful of familiar stars, the soft wash of the Milky Way. But before your mind drifts, I want to place one simple fact in front of you, one that changes everything you think you know about the cosmos. Right now, 94% of the universe is forever beyond your reach. Not because it's too far, or too dim, or blocked by dust, but because space itself is expanding faster than light can cross it. Most of the galaxies that exist today have already slipped behind a horizon you will never see again. They are still out there, shining, evolving, drifting. But their light will never reach you. Not in any future the laws of physics allow. And that leaves you with one unsettling, beautiful question. If most of the universe has already disappeared from view, then what lies outside the edge of everything you can see? You might imagine a wall, or a boundary, or some cosmic border where space simply stops. But the truth is stranger. The edge of the universe isn't a place. It's a limit created by time, expansion, and the speed of light tangled together. You live inside a fading circle of visibility, an island of ancient photons slowly drowning in an ocean that grows larger every second. The oldest light you can detect began its journey 13.8 billion years ago. Since then, the universe has stretched the distance between you and its origin to more than 46 billion light years. You're not seeing where things are. You're seeing where they were. Long before Earth even existed, long before the sun was born, long before anything that feels familiar took shape. Everything you know is built from the faintest, thinnest echo of a deeper reality. And somewhere beyond that soft circle of light, the universe continues, quietly, endlessly, in ways we can barely begin to imagine. Is it infinite? Is it curved? Is it part of a multiverse where entire realms branch and bubble like foam? Does it touch higher dimensions, slipping into directions you can't point to? Or is all of it, everything you see and everything you don't, only one layer of something far larger? Tonight, you drift toward that question, gently, calmly, with the kind of curiosity that only grows stronger as the world around you settles down. You won't rush. You won't struggle. You'll simply follow the dim circle of light to its edge, and then step into the unknown just beyond it. Your journey begins now. When you picture the universe, you might imagine everything you've ever seen in documentaries, star maps, deep field images, and night skies. Dusty spiral galaxies, clusters floating like islands, and the quiet glow of the cosmic microwave background. But the first thing you need to understand tonight is this. The universe you can observe is not the universe you live in, not even close. What you call the observable universe is simply the region where light has had enough time to reach you since the moment the cosmos began. And that region forms a sphere, centered on you, stretching roughly 46 billion light years in every direction, giving it a diameter of about 93 billion light years. It sounds unimaginably large, but this entire sphere is only a tiny patch of the deeper universe that continues far beyond anything your eyes, your telescopes, or even your imagination can reach. You aren't limited by technology. You're limited by physics itself. The universe has a speed limit, light, and a clock, the age of the cosmos. Light moves at the fastest speed allowed by nature, yet the universe has been expanding the whole time it's been traveling. So even though only 13.8 billion years have passed, light emitted from the most distant regions now arrives, from objects nearly 4 times farther away, because space has stretched underneath it. You're not seeing an edge. You're seeing the limit of time. Imagine standing on a beach at night. You see the closest waves, the shimmer of the shoreline, maybe a few boats lit in the distance. From where you stand, that faint boundary of lights feels like the end of the world, but you know the ocean continues, vast, cold, and silent, far beyond anything you can make out from shore. The observable universe works the same way. It shows you the lights closest to you across cosmic time. But the deeper ocean extends outward forever, never revealing itself. You live inside a sphere of visibility, surrounded not by walls, but by time. The farthest galaxies you detect are not where you see them. They've moved. Space has stretched. Their light began traveling toward you before Earth existed, before the sun ignited, before the Milky Way had settled into its modern shape. You're watching history frozen into the background, a museum of ancient photons carrying messages from the infant universe. But here is the part that quietly stuns you. Everything outside that sphere has never sent its light to you, not once. Those regions exist, but they are hidden behind a curtain woven from time and expansion. And beyond that curtain, the universe continues. Maybe hundreds of times larger, maybe thousands, maybe effectively infinite. No one knows. No one can know. Because the limit isn't created by the reach of your instruments. It's created by the fabric of space-time itself. Right now, as you listen, countless galaxies are moving away from you faster than light due to the accelerating expansion of space. They aren't breaking the rules. Space itself is stretching between you and them, carrying them beyond a horizon where their light can never catch up. Once they cross that line, they're still out there, but they've left your universe forever, not because they disappeared, but because the universe is expanding faster than visibility can grow. You see only a small fraction of what exists. A thin bubble of light in a realm so large, the numbers lose meaning. If the observable universe were a single grain of sand, the full universe might be the size of a beach, or a continent, or an entire planet. And even that might be too small. When astronomers say observable, they don't mean all there is. They mean all we can ever hope to see. You're boxed in not by distance, but by the combined effect of light's finite speed and the universe's relentless expansion. It's not a cage, but it is a limit, one built into the structure of reality. And this is where your sense of scale quietly collapses. The universe could be hundreds of times larger than what you can observe. It could be thousands of times larger. For all you know, the part you see is no more representative than a small droplet drifting on the surface of a vast, unbroken sea. When you step outside under the stars, everything you've ever admired, the galaxies, the clusters, the filaments, are only the lights close enough to reach you. The rest remains out there, unseen, unheard, but very real. You aren't supposed to feel small in a fearful way. You're meant to feel small in a precise way. A scientifically accurate, beautifully humbling way. Because in a universe this large, your perspective is only one window among countless windows that could exist across space and time. You're not at the center. You're at the center of what you can see. And that boundary, the edge of your observable universe, is not a wall. It's a timestamp. The light that hasn't reached you yet is not forbidden. It's simply too young, too far, too stretched. It waits on the far side of a horizon determined not by geography, but by the cosmic age. As Neil deGrasse Tyson once said, we see only what light allows us to see. And tonight, that simple truth opens the door to everything else. Because if the observable universe, huge as it is only a vanishing bubble of ancient light, then what shaped the vastness beyond it? When you imagine the beginning of the universe, you might picture a single explosion, a bright, expanding fireball rushing outward into emptiness. But the true story of the beginning is far stranger, far more extreme, and far more consequential than any explosion you've ever seen. To understand what might exist beyond the edge of your universe, you first need to understand the moment when the universe itself outran every limit we normally imagine. Right after the Big Bang, so early it defies intuition, about 10:32 seconds after the beginning, something extraordinary happened. Space didn't just expand. It surged, it ballooned, it swelled faster than the speed of light by an unimaginable factor. In that tiny sliver of time, the universe grew from smaller than a proton to something macroscopic enough to contain galaxies billions of years later. This brief but dramatic episode is called inflation. And without it, nothing you know. No stars, no planets, no galaxies, no you could exist. To picture inflation, imagine holding an uninflated balloon covered in tiny ink dots. When the balloon is small, the dots cluster closely together. As you blow air into it, the dots stretch apart. During cosmic inflation, the fabric of space stretched in the same way. But the speed and scale were incomparably more extreme. In a blink, all the quantum jitters, the irregularities built into the universe at its smallest scales, were pulled across cosmic distances. These little fluctuations became the seeds that gravity later grew into galaxies, clusters, and the large-scale structure of everything around you. But here's the part that deepens the mystery. Inflation didn't happen uniformly everywhere. It didn't turn off all at once. In some regions, inflation stopped early. In others, it continued longer. And in some corners of the cosmic landscape, it never stopped at all. This is where the idea of eternal inflation begins. When physicists realized that inflation could continue forever in some regions, they understood that our entire observable universe might just be a single pocket, one calm bubble, inside a far larger, ever-expanding sea of inflating space. Think of bubbles forming in a pot of boiling water. One bubble pops here, another there. Each bubble is separate, distinct, and sealed from the others. Now, scale that vision to the size of reality. As inflation proceeds, pockets of space peel off from the inflating background. Each pocket cools, stabilizes, and becomes a universe with its own laws, its own particles, its own cosmic story. These pockets are sometimes called pocket universes or bubble universes. And the inflating space around them just keeps growing, creating more and more bubbles in an ever-expanding foam. This is the essence of eternal inflation. While bubble universes like ours continue evolving, the deeper fabric of reality keeps expanding, generating new bubbles endlessly. And here's the part that turns curiosity into awe. If this picture is correct, there may be infinite universes expanding right beside yours. Universes with different physics, different histories, and different possibilities. But you'll never see them, and they'll never see you. No light can pass between two bubble universes, because the inflating space between them pushes them apart faster than light can travel. They are completely sealed off, isolated realms drifting inside a larger cosmic ocean. It's not that these universes are far away. It's that they exist in regions of space-time fundamentally disconnected from yours. For a moment, let your mind rest on that. You aren't living inside the universe. You're living inside a universe. One bubble, one pocket, one cooled down region of a far larger, far stranger domain. Now think about what that implies. The properties you see as universal, the speed of light, the strength of gravity, the masses of particles, may not be universal at all. They may simply be local rules for your bubble. In another bubble, gravity could be stronger, light could move differently, atoms could assemble into unfamiliar forms, or perhaps no atoms form at all. You were born inside one set of cosmic conditions, because this is the bubble where those conditions allowed stars and planets and life to exist. But there may be countless other bubbles, some sterile, some wild, some unimaginably exotic, expanding alongside yours, forever beyond your reach. Eternal inflation turns the universe from a single story into a vast library. And you occupy one book in the collection, one volume among perhaps an infinite number. This idea didn't come from science fiction. It came from the mathematics that describe inflation. The same mathematics that predict the cosmic microwave background, the distribution of galaxies, and the shape of the universe itself. When physicists ran the equations forward, the result was clear. If inflation happened, and all evidence suggests it did, then eternal inflation is almost impossible to avoid. Alan Guth, one of the founders of inflation theory, once said, "Eternal inflation suggests our universe is not the whole story." And he meant it literally. If inflation continues in even a single region, then the creation of bubble universes goes on without end, filling space-time with an ever-growing foam of independent cosmic realms. This is where the sense of scale you built in the previous segment begins to expand even further. Before, you understood that your observable universe is only a fraction of the full universe. Now, you begin to see that even the full universe might be only a fraction of something larger still. Take a breath here. Let the thought settle. It's easy to feel overwhelmed when the scale keeps expanding, but at the same time, there's a strange comfort in it. If your universe is a bubble, it means you're part of a reality big enough to make even the cosmos feel small. And in that vastness, your bubble is stable, calm, and quiet enough to support life, a remarkable rarity in the larger landscape. Eternal inflation is the point where cosmology becomes something more than science. It becomes a window into a structure so large, so rich, and so varied that even the idea of everything feels too small to describe it. It tells you that the universe you know is just one expression of a deeper mechanism that never stops creating, never stops expanding, never stops generating new beginnings. You are living in one bubble among infinite bubbles, surrounded by a cosmic sea, forever beyond your reach, forever growing, forever spawning new universes. And if that is true, then your universe is only the beginning of the story. But now, a new question appears. If our universe is only one bubble, what is the shape of the space containing them? After drifting through the strange possibilities of inflation and realizing your universe may be only one bubble in a vast cosmic foam, you return to something closer, something quieter, the shape of the space you actually inhabit. If you could pause time, step outside your galaxy, and move freely through the cosmic fabric itself, what would that fabric look like? Would it stretch on forever in every direction? Would it bend? Would it wrap around on itself? Or would you eventually reach some kind of wall? According to the best measurements from missions like WMAP and Planck, space, on the largest scales, appears to be remarkably flat. Not flat like a sheet of paper, but flat in the geometric sense. Parallel lines don't converge. Triangles add up the way you expect. And the universe doesn't curl sharply inward or outward. It's smooth, steady, and surprisingly uniform. But here's where things get interesting. A flat appearance doesn't tell you the full story. The geometry of the universe could still fall into one of three possibilities, and each one feels like a different kind of dream. The first possibility is that the universe is truly infinite, stretching endlessly in every direction, with no boundary, no outer shell, and no limit to how far you could travel. If that's the case, then your observable bubble is just one tiny spotlight sweeping across an infinite night. Everywhere outside its glow, the universe simply continues. The second possibility is even stranger. The universe could be finite but unbounded. This is a concept that bends your intuition. To picture it, imagine standing on Earth. You know Earth is finite. It has a fixed surface area. But if you start walking east and never stop, you'll never fall off a cliff or reach an edge. You'll just keep going, eventually looping around to where you began without ever encountering a wall. Space could work exactly the same way, but in 3 dimensions instead of 2. You could travel in a perfectly straight line for billions of years and eventually return to the same region of space without ever finding a border. No walls, no edge, no boundary, just curvature. The third possibility is a universe that's slightly curved, positive or negative, so gently that our instruments haven't yet detected the bending. If the curvature is incredibly mild, the universe might appear flat to us even if it's subtly shaped. The way Earth looks flat when you're standing on the ground. Only when you zoom out far enough does the curvature reveal itself. But no matter which of these 3 shapes is true, one thing becomes clear. Space might not have any physical edge at all. There is no cosmic cliff to fall from, no outer shell you can touch, no frontier where space suddenly stops and something else begins. The universe, in this sense, has no walls, only continuation or curvature. Let yourself breathe into that idea. It's lighter than the wild physics of inflation, but it settles deeper. It tells you that the cosmos doesn't need a perimeter to be complete. It isn't a box or a sphere or a container. It's a geometric field that wraps, stretches, and flows in ways your instincts were never built to follow. And even if the universe is finite, that doesn't make it small. a finite universe can still be unimaginably vast. Vast enough that you would never make a full loop, not even if you traveled for trillions of years. The absence of an edge doesn't shrink the universe, it frees it. Stephen Hawking once put it simply: the universe might be finite, but unbounded. And that short sentence carries the weight of everything you're feeling right now. Space can be complete without ever needing to end. So where does the edge come from? If space has no wall, if the geometry can loop or stretch or curve forever, if there's no border to push against, then why do you experience an edge at all? The answer is that the edge you sense isn't shaped by distance or geometry. It's shaped by something else entirely, something more subtle than curvature and more limiting than infinity. Because even if space has no boundary, your view of it does. The true edge of your universe isn't a place where space ends. It's a moment in time, a horizon defined not by distance, but by the age of the cosmos and the reach of light. And that edge is where your journey moves next. When you think about an edge, you imagine a border, something physical, a cliff where the ground stops, a wall where the room ends, a shoreline where land meets sea. But the universe doesn't work that way. Its edge is not a place you can travel to. It's not a boundary you can touch. It's something far more subtle, woven from the limits of light and the age of everything around you. To understand this edge, you need to imagine the universe not as a container, but as a room filled with darkness. In that darkness, light behaves like a flashlight beam, revealing only what it has had enough time to reach. Wherever the light has arrived becomes visible. Wherever it hasn't is hidden, not because it isn't there, but because the light simply hasn't made the journey. This is your first horizon, the particle horizon. It marks the farthest distance from which any light has had time to reach you since the universe began. Beyond that horizon, the universe continues, but it remains forever unseen because its light hasn't arrived yet, not even once. You're looking at the limit of the past. But there's another horizon, one even stranger. Because the universe isn't just expanding, it's expanding faster and faster. Space itself is stretching at an accelerating rate. And that means some galaxies are being carried away from you faster than light can travel. Not because they're breaking the speed limit, but because the road beneath them, the fabric of space, is lengthening faster than their light can bridge it. This gives you the second horizon, the cosmic event horizon. This boundary marks the distance beyond which any light emitted today will never reach you, not even if the universe lasts forever. These galaxies aren't gone, but they are slipping into a realm where their future light cannot keep up with the expansion. They fade, not in brightness, but in reach. Some galaxies are visible to you right now, only because their ancient light is just arriving. But their new light, emitted at this moment, will never make it to your universe. You are watching their past, even as their present disappears, behind an unreachable horizon. As time passes, more and more galaxies join this fate. They stretch into the dark, swept away by a rising tide of accelerating space. For a moment, let that sink in. There are galaxies you can see today, beautiful, distant, ghostly spirals, whose future light will never reach your eyes again. Eventually, their last photons will arrive, and then they will fade from your universe forever. Not because they blinked out, but because space pulled them beyond your horizon. This is why the edge of the universe is not a wall. It's a limit of light. And this is why the universe feels so strange. Its boundaries are written in time, not in space. Think again of the dark room. Your flashlight reveals a circle around you. As long as your beam moves at a fixed speed, the longer the room has existed, the farther your light can stretch. But if the darkness itself starts stretching, if the room expands underneath the light, then some parts of the room will move away faster than your light can reach them. Even if your flashlight shines forever, those regions remain in shadow. You don't need equations to understand this. You only need to know that the speed of light is the ultimate limit, and that the universe has been expanding since the moment it began. Everything you see is shaped and framed by that race between light and expansion. When you look at the cosmic microwave background, the oldest light in the universe, you're seeing the farthest the past allows. When you look at the most distant galaxies, you're seeing the farthest the future permits. In both cases, light defines the edge. Sean Carroll once said, "The horizon is a limit of knowledge, not of existence." And that line captures the quiet truth about the cosmos. The universe doesn't end where you stop seeing it. Your sight ends. Your reach ends. The universe does not. Let yourself breathe here. The idea might feel a little sad, like watching distant ships sail away, knowing they will never return. But it also brings a strange calm. The universe is not confined. It isn't boxed in. It doesn't need boundaries. It simply expands, quietly, steadily, carrying distant galaxies into a realm beyond your knowing, while still leaving you with the light they sent long ago. And that brings you to a deeper realization. The edge of your universe is not the edge of all universes. It's just the edge of what light, bound by time and expansion, can deliver to you. But if the horizons you see are limits of observation, not existence, if entire regions of space lie permanently beyond your reach, if light itself cannot carry information across these boundaries, then perhaps there are realms beyond every horizon you can imagine. Regions that don't just lie outside your visible universe, but beyond any universe like yours at all. And that question leads you somewhere even stranger. You've already seen how inflation transforms the early universe into something far more dramatic than a simple explosion. But now, you enter a territory even stranger. One where our universe is not alone, not singular, not even central. Instead, it becomes one sphere among countless spheres, all drifting silently through a vast and expanding cosmic sea. This is the realm of bubble universes. To understand why this idea emerges so naturally from inflation, imagine the early universe again. An ocean of space expanding at tremendous speed. Inflation doesn't switch off everywhere at once. Instead, it shuts down in patches, like tiny calm pockets forming inside a storm. Each of these calm pockets cools, stabilizes, and begins evolving according to its own physical rules. These pockets are the bubble universes, and your universe is only one of them. Picture a pot of boiling water. Bubbles appear in random places. Some grow fast, some shrink, some merge, others drift apart. But the boiling water underneath keeps churning, constantly creating more bubbles. Now stretch this idea beyond imagery. Replace water with inflating space. Replace bubbles with entire universes. and replace boiling with a process that never ends. While your bubble universe cooled and slowed, allowing stars, galaxies, and life to form, the deeper space around it kept expanding, generating new bubbles in a never-ending cascade. This is the multiverse as predicted by eternal inflation, a foam of universes expanding in all directions, each sealed off from the others. And here's what makes the idea irresistible to physicists. It is not an optional add-on. It is the natural consequence of inflation itself. If inflation occurred, and all evidence points to it, then bubble universes are almost unavoidable. You might wonder, if there are other universes, could we ever detect them? Could their existence leave a mark on our own sky? Some researchers believe the answer might be yes. Although bubble universes are separated by inflating space, making it impossible for light to pass between them, it is possible that in the earliest moments, when the bubbles were forming, some of them may have collided. Imagine two cosmic spheres expanding into each other. The collision would release energy, distort space-time, and potentially leave a measurable imprint on the cosmic microwave background, the faint glow left from the early universe. And here is where your curiosity spikes. Some unusual features in the CMB have already been found. Anomalies that don't perfectly fit the standard model. One of these anomalies is a series of circular patterns, cold and warm rings, that appear more orderly than random noise should allow. Some scientists propose that these rings could be scars left by a collision between our bubble universe and another one long ago. It's speculative, but not baseless. The physics of inflation allows it, and the data from satellites like WMAP and Planck leave a small, intriguing door open. Another anomaly is the mysterious cold spot, a region of the sky that is colder and larger than theory predicts. While there are alternative explanations, such as a massive supervoid, some physicists suggest the cold spot could also be a bruise left from an ancient bubble collision, a fingerprint from a universe that touched ours before drifting away forever. No one claims these anomalies are proof, but they are the kind of clues you expect from a grand story still unfolding, and they add a new layer to your sense of wonder. What if our sky carries scars from another universe? For now, science cannot confirm the multiverse. But inflation makes it the most mathematically natural answer. The idea solves several deep puzzles. Why the cosmos looks so uniform, why its structure follows a predictable pattern, and why the laws of physics seem finely tuned for the existence of stars and planets. In a multiverse, every universe has its own physical settings. Most bubbles may be sterile. Some may expand too fast for galaxies to form. Others may collapse immediately. But in at least a few bubbles, like yours, the conditions allow stars, atoms, chemistry, and life. This doesn't make your universe less special. It makes it more remarkable. Out of infinite possibilities, you inhabit one bubble where everything came together just right. And the existence of other bubbles doesn't diminish the beauty of yours. It amplifies it. Let yourself breathe here. You're drifting deeper into ideas that few people take time to contemplate. You're looking at the universe from a perspective that stretches beyond galaxies, beyond horizons, beyond the boundaries of everything familiar. The multiverse isn't meant to make you feel small. It's meant to make you feel part of something much larger than any one universe can contain. Andre Linde, one of the pioneers of inflation theory, once said, "Collisions between bubble universes may leave circular imprints." He wasn't being poetic. He was describing a real scientific possibility, a bridge between imagination and observation. In this view, the multiverse becomes more than speculation. It becomes a plausible, even likely extension of the physics we already understand. If space continues inflating between bubbles, new universes will form forever. If inflation in some regions never ends, reality becomes an infinite fractal of cosmic births. And somewhere in that endless foam, your bubble drifts quietly, self-contained, luminous, filled with galaxies and the soft glow of background radiation. A calm pocket in a storm that never stops. But this journey isn't ending here. You've explored universes that form like bubbles in an expanding ocean. Now it's time to step into an idea even more unusual. One where the universe itself might be a surface floating in a higher dimensional space. After drifting through the idea of bubble universes, vast cosmic spheres expanding within an ever-growing sea, you now step into an even stranger landscape. A landscape where the universe isn't a bubble at all, but a surface, a floating sheet, a membrane drifting through a hidden arena of higher dimensions. This is the world of brain cosmology. In string theory and its extended models, every object in the universe, every particle, force, and field is described not just by points or lines, but by vibrating strings and higher dimensional surfaces. One of these surfaces is called a brane, short for membrane. A brane can have many dimensions, but the one relevant to you is a three-dimensional brane, a 3D surface that contains everything you can see, touch, or experience. Your entire universe lives on this surface. Picture a sheet of fabric floating gently in the air. On that sheet, ants walk in every direction, forward, backward, left, right. They can cross the entire sheet, but they can never step off it. They can't jump into the space above or below. Their world is locked to the sheet. You are those ants. Your universe is the sheet, and the space above and below, the higher dimensional region surrounding the sheet, is called the bulk. The bulk might contain many dimensions, far more than the three you experience. You can't move into these dimensions. You can't see into them. You can't even point toward them. But according to many theoretical models, these dimensions might be just as real as the length, width, and height you move through every day. Inside this framework, the edge of your universe stops being a physical boundary. Instead, it's simply the boundary of the brain itself, the outer limits of a 3D surface floating in a much larger, invisible space. And here's the part that tilts your imagination. Your universe might not be the only brain in the bulk. There could be other brains, other 3D worlds, floating parallel to yours, separated not by miles, but by a tiny distance in a direction you have no way to point toward. These parallel brains could be micrometers away, or millimeters, or a fraction of a millimeter, unimaginably close, yet forever unreachable. Entire galaxies, stars, and civilizations could exist on those brains, separated from you by a dimension you can't perceive. You wouldn't see them. They wouldn't see you. Light cannot travel between brains. Electromagnetism, the force behind sight, cannot reach across that hidden dimension. but one force might: gravity. In brain theory, gravity has a unique property. It isn't confined to the brain the way other forces are. Instead, gravity is allowed to leak into the higher dimensional bulk. It can drift, diffuse, and spread into the hidden space around the brain. This is why gravity seems so weak compared to other forces, why it barely competes with magnetism, why a small fridge magnet can lift a paperclip against the pull of an entire planet. According to this idea, gravity feels weak, not because it is inherently weak, but because most of it flows out of your brain into the surrounding dimensions. This gives you something profound, a physical reason to suspect that extra dimensions might be real. If gravity is diluted across unseen dimensions, then the behavior of gravity in your universe becomes a clue, a trail of breadcrumbs leading into the bulk. And if gravity leaks outward, then it might also be influenced by objects, perhaps even galaxies, from neighboring brains, drifting parallel to your own. Picture two enormous sheets floating side by side in a vast invisible sea. They never touch, never blend, never share light, but they can tug on each other through gravity. Not enough to tear or collide at ordinary times, but enough to suggest that what happens on one sheet might subtly affect the other. For your imagination, pause and let that sink in. There may be another universe just millimeters away, in a direction you cannot point to, not separated by distance as you understand it, but by a dimension your senses cannot detect. This isn't speculation pulled from fantasy. It emerges mathematically from the same frameworks that attempt to unify all the forces of nature. In this picture, your universe is not the totality of existence. It is just one surface, one face, within a far larger structure, a brain, drifting like a silent raft across a higher dimensional ocean. And the reason you cannot see beyond it is not because nothing lies there, but because your biology, your physics, and your senses are bound to the sheet you inhabit. If you tried to step off your brain, you wouldn't fall. You wouldn't fly. You wouldn't move into some cosmic abyss. Instead, you would simply cease to exist in any meaningful physical sense. You are made of particles confined to the brain. You cannot leave it any more than a shadow can detach from the surface it's cast upon. The edge of your universe, then, is not truly an edge at all. It's simply the limit of the surface you exist on. The bulk beyond that surface might extend infinitely. Other brains might float through it. Other universes might glide silently nearby. But you walk only within the sheet that gave birth to your matter and your physics. You breathe. You imagine. You exist because this brain allows it. Lisa Randall, one of the physicists behind modern brain theory, summarized it elegantly. Our universe might be just a floating brain in a higher dimensional sea. Once you accept that, a new question forms, one stranger, deeper, and more dramatic. If brains drift through a higher dimensional space, what happens when they finally collide? The next idea you encounter builds directly on this moment. An idea bold enough to rewrite the origin of everything. You've pictured the universe as a bubble among countless bubbles. You've imagined it as a floating sheet drifting through a higher dimensional sea. Now those ideas converge into one of the most striking possibilities ever proposed. The idea that your universe was born, not from a single explosion, but from a cosmic collision. This is the heart of the ekpyrotic universe, a model suggesting that the Big Bang was not truly a beginning, but an event. One chapter in an infinite cycle that stretches backward and forward through time. To understand this idea, return to the vision of brains, enormous three-dimensional sheets floating in a higher dimensional bulk. These sheets are not fixed. They move, they drift, they can stretch, bend, and ripple across dimensions you cannot perceive. And just like any objects drifting in a vast space, brains can draw closer to one another. Now imagine two such brains slowly approaching. For eons, trillions of years, they drift through the bulk. They are utterly silent, dark, featureless to any inhabitant living within them. But as they draw closer, enormous gravitational tension builds between the brains. Their surfaces begin to ripple. Energy accumulates across their dimensions, until finally, inevitably, they collide. And in that moment, everything changes. To you, living inside one of the brains, the collision would not feel like two cosmic sheets striking each other. Instead, it would appear as an unimaginably hot, dense flash of energy, an event you would describe as a Big Bang. Matter would surge into existence. Space would expand. Particles would form. Photons would stream outward. Galaxies would eventually take shape. But in this model, the Big Bang is not an explosion from a singular point. It is the release of energy when two vast surfaces hit and rebound. You can picture it easily. Two giant trampolines colliding and then springing apart. The impact creates waves and heat. The separation creates space to cool and expand. Everything that follows, the birth of stars, the rise of heavy elements, the formation of planets, are aftershocks of that cosmic impact. In the ekpyrotic view, your universe expands after the brains bounce apart. Over trillions of years, expansion slows, gravity tightens. The brain begins to contract again, gradually drifting back toward its partner brain. And eventually, after unimaginable stretches of time, they collide once more. The universe resets. The cycle begins again. No absolute beginning, no final end, only rhythm, a cosmic heartbeat. This perspective does something profound. It dissolves the idea of a singular origin, an initial moment from which everything sprang. Instead, it paints the universe as part of a larger, eternal process, an infinite loop of creation and renewal, a sequence of expansions and contractions, collisions and rebounds, births and rebirths. Let yourself drift into that possibility. The idea that your universe is not unique, not isolated, not the first, not the last. Just one chapter in a story that has no first page. What makes the ekpyrotic model compelling is not just its philosophical beauty. It also offers practical scientific advantages. For instance, it gives an elegant way to avoid the initial singularity, the infinitely dense point required by the traditional Big Bang model. Instead of asking how the universe emerged from a physical impossibility, the ekpyrotic view replaces that singularity with a collision, something far easier to frame within known physics. The model also offers potential explanations for certain anomalies in the cosmic microwave background, subtle patterns that don't fit perfectly with the standard cosmological picture. Some versions of the theory even help address the long-standing puzzle of why matter vastly dominates over antimatter, a mystery that has resisted explanation for decades. The more you follow the idea, the more it begins to feel strangely natural. Maybe the universe behaves not like a firework, but like a tide. Not a one-time event, but an eternal rhythm. Not a beginning, but a beat. Let the thought settle for a moment. It softens the harshness of a universe that starts from nothing. It replaces that nothingness with motion. It replaces mystery with pattern. It replaces beginning with continuity. Paul Steinhardt, one of the architects of the ekpyrotic model, once said, "The universe may be part of an infinite cycle of collisions." It's a line that widens your idea of existence. If true, then the cosmos doesn't just expand. It pulses. It breathes. And if the Big Bang was only one collision in an endless sequence, then what you call the beginning of everything may have simply been the beginning of your turn. The ekpyrotic universe doesn't dismiss the Big Bang. It reframes it. It tells you that the blast you think of as the birth of space and time was actually the flare of energy released when two higher dimensional sheets touched. What you call creation is just the moment two worlds kissed. But to understand collisions fully, to understand how brains drift, approach, and collide, you must understand the space they move within. Because behind every collision lies something deeper, something wider, something more mysterious than the brains themselves, the higher dimensional bulk. And that is where you go next. Until now, you've imagined universes as bubbles, as sheets, as drifting surfaces colliding in a higher dimensional sea. But to truly understand where those brains float and why universes might exist side by side, you have to step into one of the most mind-stretching ideas in modern physics: dimensions beyond the three you live in. Every day, without thinking, you move through three familiar directions: forward and backward, left and right, up and down. These three axes build the world you know. Everything you can see, touch, and navigate fits inside this framework. But physics suggests that these three directions may only be part of a much larger structure, one that includes hidden dimensions, folded so tightly or stretched so strangely that your senses cannot perceive them. There are two broad possibilities. The first is the idea of compact extra dimensions, tiny curled-up spaces known as Calabi-Yau manifolds. These shapes are so small, so tightly folded, that even the smallest particles cannot move through them. To visualize this, imagine an ant walking along a long rope. From far away, the rope looks like a one-dimensional line. But up close, the ant sees the rope's full structure, the little circle of fibers wrapping around. In the same way, your universe might appear 3D, but beneath that appearance could lie tiny curled-up dimensions that only reveal themselves at unimaginably small scales. The second possibility is even more dramatic: large extra dimensions. These are hidden directions big enough for gravity to leak into, and big enough to hold entire brains floating parallel to your own. If you could move through these dimensions, even by a fraction of an inch, you might pass from your universe into another. But because all matter and light are bound to the brain, you never drift off into those hidden spaces. They exist beside you, all around you, yet forever outside your reach. These extra dimensions help solve a deep puzzle. Why is gravity so much weaker than the other forces? A small magnet can lift a metal paperclip against the pull of an entire planet. Gravity seems feeble. But if gravity bleeds into extra dimensions, if it spreads out beyond your brain, then what you experience is only a fraction of its true strength. The rest is dispersed into directions you cannot see. This possibility brings hidden dimensions into the realm of testable physics. If gravity behaves slightly differently at extremely small distances, that might be the signature of extra-dimensional leakage. Now imagine that these dimensions are large enough, extended enough, to allow entire bypass routes between universes. Instead of thinking of an outside to the universe in the traditional sense, imagine sideways directions that slip between brains. The edge of your universe, then, is not a wall, but a fold, a wrinkle created by a dimension that curves beyond your perception. This is the part where your imagination gently tilts sideways. You cannot point toward these dimensions. You cannot walk into them. Your biology is bound to the brain. Your perception is confined to the three-dimensional slice you inhabit. But the higher dimensions might still be there, silent, invisible, real. And if they are real, then the universe becomes more mysterious than any map suggests. Some universes might be incredibly close, just millimeters away, but separated by a direction your mind cannot grasp. In these neighboring brains, galaxies could whirl, stars could burn, and maybe even life could evolve, never knowing how near we are. Like two cities built on opposite sides of a sheet of paper, separated not by miles, but by a single fold. Let that image rest with you. Some universes may be just a fraction of an inch away, in a direction you can't point to. This does not mean you can step out of your universe. It means that outside may not be a direction at all. Instead of reaching beyond the universe, the path forward could be a path sideways, slipping into hidden dimensions that your senses were never built to detect. Michio Kaku captured the idea simply. Extra dimensions may not be small. They may be right next to us. Once you accept that possibility, everything changes. The universe stops being a closed 3D bubble. It becomes a slice of a much grander geometric structure, one that includes directions, spaces, and pathways beyond your intuition. And with that wider view comes a new question. If dimensions shape the motion of brains, if brains drift, bend, and collide within a higher dimensional space, if time itself emerges from the way these dimensions unfold, then what happens when you look at symmetry, the deep patterns that shape the entire cosmos? Because once symmetry enters the picture, you discover something even stranger. Time might have a mirror, and that is where your journey turns next. Up to now, you've explored universes beside ours, brains drifting in higher dimensions, and collisions that may repeat forever. But the next idea doesn't place another universe beside ours. It places one behind ours, mirrored across the moment of creation like a reflection across a cosmic dividing line. This is the CPT symmetric universe, an idea so elegant and so unsettling that it shifts not only how you imagine space, but how you imagine time itself. In physics, three fundamental symmetries describe how nature behaves: C for charge, P for parity, mirror reflection, T for time reversal. If you flip all three at once, CPT, the laws of physics remain perfectly consistent. This is one of the deepest principles known. And some physicists have taken this symmetry to its logical extreme. If the universe must obey CPT symmetry, then the universe itself may require a partner, a twin, born in the same moment as ours. Imagine the Big Bang, as a single event, a central point where two universes unfurl in opposite directions. Ours expands toward positive time. The other expands toward negative time. Two cosmic branches spreading from one trunk, moving away from each other not through space, but through time's arrow. This twin universe is sometimes called the anti-universe, not because it is evil or destructive, but because its properties mirror ours with mathematical precision. In this anti-universe, time flows in the opposite direction, charges are reversed, and motion itself unfolds according to inverted physics that remain fully consistent with the laws we observe. You can think of it like this. If our universe is the forward stroke of time's brush, the anti-universe is the backward stroke, completing the cosmic symmetry. Let yourself pause there. Let the thought settle. There may be a universe where time flows backward, not metaphorically, literally. From our perspective, its timeline runs the wrong way. From its own perspective, we are the ones running backward. In that universe, stars form as its time increases in its direction. Galaxies evolve, structures emerge, all perfectly natural from its point of view. But none of its light, particles, or signals can ever reach us. The two universes are not parallel in space. They are symmetric across time. They split at the Big Bang and have been diverging ever since. Though completely separate, this anti-universe could solve several puzzles that trouble the standard cosmological model. First, why does matter dominate over antimatter? Right after the Big Bang, the laws of physics suggest matter, and antimatter should have formed in equal amounts. But our universe contains far more matter. According to the CPT symmetric model, the anti-universe carries the missing antimatter, but arranged in a way that maintains perfect overall balance across the full CPT symmetric whole. Second, why do neutrinos have such tiny masses? The math predicts that in the anti-universe, neutrinos would be right-handed, that is, spinning in the opposite orientation of ours. These right-handed neutrinos are invisible to us because they barely interact with ordinary matter. But their existence would neatly explain why the neutrinos we see have such small but non-zero masses, a persistent mystery in physics. Third, how smooth and symmetric is the Big Bang? The CPT model provides a natural explanation. If the universe and anti-universe emerge together from the same point in perfect mirror balance, that symmetry would imprint itself on the earliest conditions of both universes. The Big Bang stops being a chaotic starting point and becomes a smooth junction between two opposing timelines. This idea isn't wild speculation. It's built on strong mathematical footing, supported by work from Neil Turok, Latham Boyle, and other leading theorists. It doesn't require unknown inflation fields or hypothetical exotic energies. It simply applies the deepest symmetry in physics, CPT, to the universe as a whole. And though the anti-universe can never interact with ours, it might leave subtle fingerprints, some characteristics of the cosmic microwave background, the evenness of its distribution, the lack of certain expected asymmetries, fit neatly into a CPT symmetric picture. A few unusual features might point towards such a mirror partner woven into the fabric of cosmic birth. If this idea is correct, the Big Bang was not a single explosion at the beginning of time. It was a mirror, as Neil Turok once put it, a reflection point between two expanding universes. two realities born together, diverging endlessly. Think about that for a moment. The answers you seek about the universe's birth might not be hidden in distant galaxies or deep space telescopes. They might be encoded in symmetry, in balance, in the quiet equation that says, if there is a universe with time flowing forward, there must be one with time flowing backward. This is where awe and contemplation merge. You're no longer just imagining other universes beside yours. You're imagining one behind yours, a mirror twin that completes the cosmic story in a direction you can never travel. But if twin universes can leave traces in ancient light, what about signals that ripple through space-time itself? What about waves, faint, distant, ghost-like, that might carry whispers from realms beyond everything we know? Because that's where your journey turns next. As your mind drifts through ideas of mirror universes and hidden dimensions, you reach a new kind of messenger, one that does not rely on light, particles, or any force you're familiar with. Instead, it travels as a ripple in the very fabric of space-time itself. These are gravitational waves. First predicted by Einstein a century ago, gravitational waves are not vibrations in air, not pulses of light, not particles streaming across space. They are distortions, subtle wrinkles, moving through space-time like ripples spreading across a cosmic pond. Whenever massive objects accelerate violently, two black holes merging, neutron stars spiraling together, they send out waves that stretch and squeeze the universe as they pass. But no one had ever detected them directly until 2015, when the LIGO Observatory caught the faint tremor of two colliding black holes more than 1 billion light-years away. The detection was so delicate, it measured distortions smaller than a fraction of a proton. And yet, it opened an entirely new window into reality. Because gravitational waves don't behave like light. They don't scatter. They don't dim the same way. They can pass through matter, stars, galaxies, even through entire universes, if such things exist. This makes them perfect messengers. And some theoretical models predict that if the universe has higher dimensions, brains, or neighboring bubbles, gravitational waves might carry hints of those realms. For example, some theories suggest that gravity leaking into extra dimensions could distort certain wave patterns, stretching them or weakening them in ways that ordinary physics cannot explain. Other ideas propose that if brains collide, the impact could send out gravitational echoes, waves that reflect off higher dimensional boundaries, returning with strange reverberations. And in the realm of eternal inflation, if two bubble universes once brushed against each other, the collision might send gravitational ripples through the multiverse. Those ripples could, in principle, reach us, not as light, but as faint, unusual patterns in the gravitational wave spectrum. No such signal has been found yet. But scientists are listening. They're tuning detectors to catch any wave that behaves differently than expected, any whisper that doesn't match typical black hole or neutron star mergers, even one unusual signal, one wave with properties that don't align with known astrophysics, could point to something extraordinary. A wave from another universe could be passing through us right now. Kip Thorne, one of the architects behind LIGO, put it beautifully. Gravitational waves are whispers from the dark. And those whispers may carry messages not just from distant galaxies, but from beyond the boundaries of our universe altogether. Each new detection opens space wider, revealing more than telescopes ever could. If multiverses exist, if higher dimensions are real, gravitational waves may be the first proof we ever see. But waves are not the only strange motions in the cosmos. Some galaxies appear to be drifting, not away with expansion, but towards something unseen. Something pulling on them from beyond the horizon. And that mystery takes you deeper still. By now, you've followed whispers from gravitational waves, hints from symmetry, and clues woven into the earliest light of the cosmos. But the next mystery is not a whisper. It's a motion, a vast, coordinated drift of galaxies moving in a direction that nothing inside the observable universe can explain. This is dark flow, one of the strangest and most unsettling clues in modern cosmology. Beginning with observations from the WMAP spacecraft and later refined by Planck, scientists studied the motion of galaxy clusters across billions of light years. They expected these clusters to scatter in random directions, pulled by local gravity, pushed by cosmic expansion, and stirred by the normal flow of matter across space. Instead, they found something else. Clusters across a region 2.5 billion light-years wide, containing hundreds of thousands of galaxies, were all moving together. Not slowly, not randomly, but in a single, coherent direction. A bulk flow, a cosmic current. These clusters appear to be drifting at speeds between 600 and 1,000 kilometers per second, roughly 1,000 times faster than a passenger jet, toward a region of the sky where there is nothing. No supercluster, no overdensity, no massive structure inside the observable universe large enough to pull them. This behavior does not fit the standard cosmological model, LCDM, even when you account for dark energy, cosmic expansion, and the large-scale web of galaxies. According to everything we understand about gravity, matter distribution, and the shape of the universe, this motion should not exist, and yet it does. Two major hypotheses attempt to explain dark flow. 1. A gigantic structure outside the observable universe is pulling on us. If something truly enormous, perhaps a supercluster or megavoid far beyond our horizon, exerts gravitational influence, it could tug on the galaxies within our visible bubble. But because the source lies beyond the event horizon, it cannot be seen. Its light has never reached us and never will. We feel its pull without ever glimpsing its shape. It would be like standing on an island at night, watching waves move toward an unseen shoreline you will never reach. 2. A remnant collision with another universe. The second explanation pushes deeper into the multiverse. If our observable universe once brushed against a neighboring bubble universe during the earliest stages of inflation, the collision could create a permanent gravitational gradient, a tilt in space-time that still influences matter today. The clusters drifting in one direction would be following the imprint of that ancient interaction. The collision doesn't need to be ongoing. The scar left in space-time would persist, guiding clusters like leaves caught in a current. Some researchers have gone so far as to call dark flow the first empirical hint of the multiverse, a possible sign that our bubble is not alone, and that something beyond our horizon once touched us. It's a bold claim, and not universally accepted. The scientific community is sharply divided. Some studies argue that the statistical evidence is weaker than initially believed. Others defend the data, pointing to consistent patterns that appear in multiple independent analyses. For now, dark flow remains suspended between controversy and possibility, a mystery wide enough to fit multiple explanations, yet precise enough to demand one. Take a moment to picture it. Something massive, beyond everything we can see, may be pulling entire clusters of galaxies, not metaphorically, not symbolically, literally tugging on matter across billions of light years. It may be the footprint of a megastructure outside the observable universe. It may be a ripple left by a cosmic collision. It may be an imprint from a neighboring bubble universe in the earliest moments of creation. Or it may be something even stranger, something your imagination hasn't reached yet. Whatever it is, dark flow is a quiet reminder that the universe is not a closed room. It's an open landscape whose true extent remains hidden by the limits of light and time. You're not looking at a sealed container. You're looking at a horizon, an observational boundary pressed against something larger. Alexander Kashlinsky, who led some of the key analyses, put it simply: dark flow might be our first glimpse of the greater cosmic landscape. Let that thought settle. It changes the way you picture the universe. It changes the feeling of the night sky. Behind the calm stars, behind the silent galaxies, behind the cosmic microwave background itself, there may be motion driven by something beyond the visible realms. And dark flow isn't the only strange imprint on the sky. Some shadows are far older, more ancient than any galaxy. Shadows etched into the universe when it was only a few 100,000 years old. And one of those shadows has puzzled cosmologists for decades. After following dark flow across billions of light years, after watching entire clusters drift towards something unseen, you now turn your attention to a mystery far more ancient. A mystery etched not into galaxies or clusters, but into the oldest light in the cosmos. A mark so large, so faint, and so inexplicable that for nearly 2 decades, it has sparked debates, theories, and whispers about what might lie beyond our universe. This is the cold spot, a strange, chilling blemish on the map of the cosmic microwave background, the faint afterglow of the Big Bang. The CMB is the universe's oldest photograph, a snapshot of the cosmos when it was only about 380,000 years old. It is nearly uniform in every direction, almost perfectly smooth, varying in temperature by only a few millionths of a degree. But on that serene backdrop lies a region that stands out dramatically, a vast, unusually cold patch stretching nearly 1.8 billion light-years across. It is colder than the surrounding regions by an amount far greater than expected. Not slightly colder, significantly colder, uncomfortably colder. A drop so large that the odds of such a feature appearing by random chance are incredibly small. So the question becomes, why is it there? Over the years, scientists have explored several possibilities. 1. A statistical coincidence. It's possible, though unlikely, that the cold spot is just a random fluctuation in the early universe. The cosmos is vast, and randomness can produce rare events. But when you calculate the probabilities, the cold spot stands out like a bruise that shouldn't exist, a fingerprint that doesn't match the rest. 2. A supervoid, one of the largest ever discovered. Some observations suggest a massive supervoid A region with far fewer galaxies than normal lies in that direction. A supervoid can slightly cool the light passing through it by altering gravitational potential along the photon's path. And yes, a supervoid, roughly the size of this region, does appear to be present. But here's the twist. The supervoid is not large enough, deep enough, or empty enough to explain the cold spot's severity. It contributes to the cooling, but only a fraction of what is observed. The anomaly is stronger than the void can produce. It's like finding a small dent and being told it caused a massive crater. 3. A collision with another universe. This is the most provocative idea, and the one that refuses to disappear. Some cosmologists propose that the cold spot may be a scar left from a collision between our universe and another bubble universe in the early inflationary period. When such bubbles collide, they distort space-time and energy density, leaving circular imprints or large-scale temperature anomalies. The shape, size, and temperature drop of the cold spot align eerily well with some models of bubble collisions. Dr. Laura Mersini-Houghton, a physicist known for her work on the multiverse, once remarked, "The cold spot is one of the strangest features in the cosmic microwave background." And in her interpretation, the cold spot may be a birthmark, a leftover signature of another universe touching ours before drifting away forever. Think about that for a moment. The universe you see in every direction, the galaxies, the clusters, the nebulae, the voids, may carry a faint bruise from a universe that once brushed past ours. A cosmic memory, an echo, a mark so old it predates every star that has ever burned. Let that image settle. A scar on the universe's first light. If this interpretation is correct, the cold spot becomes more than a statistical oddity. It becomes evidence, faint, tentative, but compelling, that our universe may not be alone, and that it may have interacted with other universes in the earliest moments of creation. But science is careful. The data is debated. Alternative explanations remain possible. Instrumental errors, subtle physical effects, or unknown astrophysical processes might still offer answers. And yet, the cold spot persists, stable across multiple measurements, visible in data from both WMAP and Planck, unexplained by known structures, and stubbornly aligned with predictions from certain multiverse models. You don't need to accept the multiverse to appreciate the mystery. You only need to feel the weight of the unknown, the sense that the universe might hold memories beyond the reach of light, shadows cast by events that occurred before galaxies existed. As you drift deeper into the night's calm, you begin to sense something humbling. The universe is not a blank canvas. It has texture. It has history. It has scars. And beyond these strange imprints, beyond the cold spot, beyond dark flow, beyond all the hints left in ancient light, something even more humbling awaits. Something that reminds you how much of the cosmos is slipping away, unseen, over the horizon of time. Because the universe isn't just marked by anomalies. It is marked by limits, by horizons that shrink as expansion accelerates, by galaxies that vanish from our reach, by entire realms, perhaps entire universes, that lie forever beyond our light. And now you turn to that fading edge. As you drift deeper into the mysteries of the cosmos, the journey turns inward, towards something quieter, softer, and somehow more human. Not everything mysterious lies beyond the universe. Some mysteries lie in the way the universe slowly slips away from us. Because while the cosmos expands, it is not expanding gently. It is accelerating, driven by dark energy, a force we barely understand. The universe is stretching faster than light can cross it. Galaxies at great distances are being carried away on a tide of expanding space, retreating faster than their light can reach us. This means something profound, something easy to miss, but impossible to forget once you understand it. More than 90% of all galaxies are already slipping beyond our visibility forever. They are not disappearing in the way stars burn out or galaxies collide. Instead, they are being swept behind a horizon of accelerated expansion, crossing a boundary from which their light will never return. Even galaxies we can see today, delicate spirals hanging on the edge of our telescopes, will one day fade from existence, not by dying, but by outrunning the speed at which their light can travel. If you could leap forward tens of billions of years, the night sky would change in a way that feels almost sorrowful. One by one, distant galaxies would dim. Their final photons would reach us, and then they would be gone. Only a handful of the closest galaxies, those gravitationally bound to us, would remain visible. Everything else would dissolve beyond the cosmic horizon. And in that distant future, the Milky Way and Andromeda will have merged into a single giant galaxy, often called Milkdromeda. It will dominate the night sky as a great sprawling river of stars. But apart from it, the rest of the universe will be missing. The sky will go quiet, empty, a cosmic island floating alone in an ocean that no longer reveals itself. Let that image settle. In the far future, the night sky may be completely empty. Imagine stepping outside under a dark sky billions of years from now. You look up, expecting the faint shimmer of other galaxies, cascades of starlight stretching across the void. But there is nothing. Only the familiar glow of the merged Milkdromeda, and beyond that, total blackness. Future astronomers, standing under that sky, will see nothing but emptiness. No cosmic web, no expanding universe, no galaxies drifting in the distance. Without the evidence we observe today, they would have no way to infer the true nature of the cosmos. The clues that revealed the Big Bang, the redshifts, the CMB, the clustering of galaxies, all of it would be gone. Lawrence Krauss said it plainly. Future astronomers will see nothing but darkness. Those future scientists, no matter how brilliant, might never discover that the universe once held trillions of galaxies. They might never deduce expansion. They might never realize there was a beginning, or that their island galaxy is just one coast in an invisible archipelago fading beyond reach. Their entire reality would be a single glowing island in a sea of nothing. And this is where the sadness settles in. Not heavy, but quiet, like the feeling of watching a loved place slowly drift into memory. The universe is not collapsing. It is simply slipping away, carried beyond the limits of what light can show. But in that quiet sadness lies something beautiful. We are living in the lucky era, the brief cosmic moment when the skies are still full, when galaxies glow across billions of light years, when ancient light streams toward us, whispering secrets of the early cosmos, when the universe reveals itself freely. We are alive at the one time in cosmic history when beings like us can look outward and truly see the vastness beyond our home. The universe is giving us everything it has to offer: its past, its structure, its evolution. All the clues lie before us now, in this thin, fleeting slice of time. And so, as you stand under the night sky, you may feel both awe and a gentle melancholy. The stars you see today, the galaxies you observe, the cosmic landscape you marvel at, they are part of a vanishing era. We are witnesses to a universe that is slowly closing its doors. You understand now why the cosmos feels so vast, yet so fragile. Why every photon that reaches us is a gift from a world that may soon slip beyond the horizon forever. And after everything fades, after the galaxies vanish, after the night sky empties into darkness, a question remains. A question that has been waiting since the very beginning of your journey. If everything we can see is temporary, if the galaxies, the bubbles, the brains, the dimensions all slip into shadow, then what could possibly lie beyond this fading horizon? What waits on the far side of everything? You've traveled far tonight, farther than light can carry you, farther than observation can reach. You've moved through bubbles and brains, through hidden dimensions and mirrored time, through ancient scars and vanishing horizons. And now you arrive at the quiet edge of the journey, where the universe softens into possibility. What lies beyond the edge of everything you can see? Perhaps the answer is simple. If space is infinite, then there is no edge at all, no boundary, no outer shell, just an endless plain stretching in every direction, too vast for any light to cross in the lifetime of the cosmos. Or perhaps the universe is one bubble in a cosmic foam, part of an infinite sea of universes forming, expanding, and drifting through an inflating backdrop. In that view, the edge of your universe is simply the curved surface of your bubble. One sphere among countless others, each sealed away in the deeper ocean. Maybe the truth lies in the dimensions you cannot see, directions you cannot point to, invisible corridors where space folds into itself like a sheet drifting in higher dimensional air. If extra dimensions are real, then outside the universe might not be outward at all, but sideways, through pathways that your senses were never built to perceive. Or maybe the universe has a twin, a mirror counterpart born at the same moment, expanding into opposite time, balancing the cosmic equation so perfectly that the Big Bang becomes not a beginning, but a reflection. Two universes branching from one moment, moving away forever, each carrying the imprint of the other. Or, as the ekpyrotic model suggests, your universe might be one beat in an endless cycle, brains drifting, touching, rebounding, creating Big Bang after Big Bang in a rhythm older than time. In that story, the universe has no first chapter. It simply breathes. And maybe, just maybe, there is something beyond all of these ideas, a structure so different from our intuitions that no equation, no telescope, no theory has yet brushed against it. Something that doesn't fit into bubbles or brains or cycles. Something that exists not outside space, but outside understanding. That's the quiet truth you arrive at. The edge of the universe is the edge of what we can comprehend. You were born inside a faint circle of light, a tiny illuminated island within a much larger darkness. Yet from that island, you look outward, always reaching, always wondering, always pushing against the horizon of knowledge. It's what humans do, You search for edges not to touch them, but to imagine what lies beyond. And you don't need to solve the universe tonight. You don't need to reconcile every theory or answer every question. You don't need to grasp infinity before falling asleep. Just rest knowing you're part of something vast, quiet, and beautiful. Something that existed long before you and will continue long after. Something that humbles you without diminishing you. Let the possibilities drift through your mind like distant stars. Infinite space, cosmic foam, hidden dimensions, mirrored time, eternal cycles, and mysteries that lie forever beyond light. Let them float. Let them fade. Let them settle into the calm of the night. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." He didn't mean that you must chase it restlessly. He meant that wonder is always there, even in the silence, even in the dark, even at the edge. And curiosity is infinite as whatever lies beyond the universe's fading horizon. So close your eyes. Let your thoughts drift outward. Feel the vastness softening into peace. The universe is quiet tonight. You are safe within it. And the mystery will still be here when you return. Good night, traveler.